Welcome to week 2 in the class. In this recording, we'll cover how to analyze a single continuous outcome using a single explanatory variable. So the outcome would be our dependent variable. In this case, we think it's continuous. It's some kind of a number. And our explanatory variable is just a single independent variable. Multiple explanatory variables are going to be covered next week. So that means we're going to be dealing with t-tests and Mann-Whitney or Wilcoxon tests, whatever you want to call them. If we have two groups, if we have more than two groups, we can use analysis of variance, the ANOVA, or a Kruskal-Wallis test for the parametric option there. You can read the learning objectives. I trust you. Here, click this button to view the video you're already watching, so no need for that one. Let's actually click on this button over here, the practice data sets. We'll be using this to walk through how we would carry out an analysis in SPSS. So we have a plant growth data set here, a data set about the likelihood that applicants might apply to graduate school, a question type data set where we're looking at scores on multiple choice and short answer questions, and then there are the checkpoint data sets that you're going to use to demonstrate your understanding of the topic. So you'll be using these to fill out the checkpoint questions later on. Okay, let's start off with the plant growth data, and I'll just highlight the values, copy, and I'm going to paste those into SPSS. I didn't take the names because those are going to go up here and SPSS doesn't let me paste up there. So I'm going to go into the variable view and I'll change the names to what makes sense, so weight and group for my weights and groups. Weight is a scale measure, so I'll specify that here, and that's about all I need to do. Go back to the data view, things look fine. So let's go ahead and run our analysis here. So we'll go analyze, compare means and proportions, and why don't we start off with just a t-test? So we've done these before, so we can do weight as my test variable, okay, and then group will be my grouping variable, and I just need to define my groups. And for group 1, let's take control and let's do treatment 1 as my second group. I don't really need to mess with any of the options here. We run this, and here you can see it's spitting out some statistics. Great, I get my descriptive statistics. There's 10 samples in each group. I get my means, standard deviations. I see that treatment 1 has a little lower mean than control. But if I go down here, I look at my independent samples t-test. What am I looking at? Well, first there's Levine's test for equal variances. Should I assume equal variance? Yeah, that looks totally fine. So look at our p-value over here, sig. Notice it's not less than 0.05, so the variances aren't different. I can use either one of these, and when we look at their confidence intervals, hey, they're basically the same. So this is the part that matters over here. And if we look at the low end and upper end of our confidence intervals, we see that 0 is in it. Therefore, no difference. And this is, of course, supported with the p-value greater than 0.05. There's some unitless effect sizes measured here. I don't really care about those. So what have I concluded? The control and treatment 1 groups have the same mean. Okay, and I can do the same thing for control and treatment 2, treatment 1 versus treatment 2, but I shouldn't do that. And the reason for that is I'm going to inflate my type 1 error rate. No, whenever you have more than 2 groups, like we do over here, we have 3 groups, we should use an analysis of variance. And there are really 2 ways of doing an analysis of variance. You can run the analysis of variance, as it's called, or you can run a general linear model. I think that's far more useful. I'll show you both ways. First, what we need to do, though, is make sure our data are normal. Now, we know that we have independent observations. That's just how the data were collected. Measuring this plant's weight didn't influence the weight of this plant or the other. That's what it means to be independent. What we have to wonder, though, is do we have normality? Right? Can we assume a normal distribution, and can we run with these parametric t-tests or ANOVAs? So to look at that, let's go here to Analyze, Descriptive Statistics, and we'll go to the Explore window. I want to look at weight, and I want to look in the different groups do I have normality here? So I'm going to go to plots, and I'll first of all get rid of stem and leaf. I don't really find that helpful. We'll look at histograms, and we'll do some normality plots with tests. That's the key thing we want to select here. Okay, and that looks good enough to me. We won't worry about messing with too many other things. We'll click OK. Alrighty, and now we have our output here from our normality tests. Okay, so I don't care about this. I don't care about the descriptives, although they are kind of nice. That's not the whole reason I did this. I wanted to look at the normality of my data. Test for normality down here, you can see. We look at our p-values in either one of these. So there's a couple options, and neither one of them are indicating to me that I have a problem, because none of the p-values, or the sig columns here, are less than 0.05. So great, they're normal enough. Let's have a look at the histograms. Here's the control group. I know it's not a perfect bell curve, but it's good enough. And good enough for treatment 1, good enough for treatment 2. Here we can look at our QQ plot. So what we're hoping here is that as we move across here, we have about the same number of dots above as we do below. We don't see like a whole bunch of dots that are high here and really low here. This looks pretty well okay. No major deviations. Yeah, we got a couple low dots over here and here, but nothing major, right? They're following the line pretty well. Here, these detrended plots are the same thing, but instead of having a slope, they've just made the slope 0. And this is probably a slightly easier way of looking at the data. And hopefully this is a fairly straight line. Again, they're a little different up here, but nothing's too bad. And when we look at the box plots, they're pretty close to symmetric. So now what we have to wonder, is there any difference somewhere in the data? Given that these look normal enough, by inspecting our plots and looking at our tests, and we scroll back up, right, looking at both of our tests of normality here, none of them are indicating that we have a problem. I'm going to go back to the bottom, or I can click here on box plot. Are any of these different? You know, if anything, to me, treatment 1 and treatment 2 are looking pretty different. Right, the boxes are pretty well different from one another. Maybe treatment 2 and control, but the medians are actually pretty darn close. I don't know. And I haven't calibrated my visual p-valueometer lately, so I'm going to run some tests. So let's run ourselves not a whole bunch of t-tests, but instead a one-way ANOVA. Okay, so we'll head back over to our data set, and let's go analyze, compare means and proportions, and rather than stopping at the independent samples t-test, we're going to go to the one-way ANOVA. And you'll notice my group isn't here anymore. That's because of a shortcoming of SPSS. It doesn't let us put a string into our ANOVA. Don't worry, it's an easy fix. What we're going to do is transform our data. So if you find you don't see a data set that you should, just know that's SPSS's fault. Don't sweat it. Let's do an automatic recode. And what I'm going to do is take group, and I'm going to just let SPSS automatically recode it. And let's give it the new name, group recode. That way I know that this is group, but I've recoded it. And I'll click add new name. All looks good. And I'm going to click OK. And we'll let it do its thing. And look at that. Control is now 1, and treatment 1 is 2, and treatment 2 is 3. This is going to work now, because now we don't have string data. Now it's numeric. So everything should work. Let's cross our fingers and hope it does. So we'll go back to Analyze. Compare means and proportions. We'll click on our one-way ANOVA again, and look at that. We have 2 variables. Okay, my dependent variable is still weight. Group recode is now my factor. I don't really care much about the effect size. I will leave it. I just know that I won't look at it. Contrast is not particularly useful, but post hoc is. So we'll click on post hoc here, and there's a lot of post hoc tests. Now these would be the pairwise comparisons that are carried out. Essentially your t-tests that are now controlling for that type 1 error rate. And I'll just click the Bonferroni here. What this does is inflate the p-value based on how many comparisons there are. So rather than looking for 0.05, if there are 2 comparisons, we multiply that by 2. I'm sorry, we divide that by 2. And now we're looking for 0.025. Okay, so it's a very simple correction. There are a lot of options. Tukey is a classic. You can go with that if you want. I won't in this case. And I will just say continue. Okay, so now at this point, we can run ourselves a one-way ANOVA. We'll click OK, and we are greeted with this analysis of variance table. And this is looking at the variance, the mean square here, between groups compared to within groups. And notice we've got a lot more between than within. We do a little division here, get that F statistic, and that's the basis for our p-value shown on the right. Notice less than 0.05, so we reject the null. There's a difference somewhere in here. I don't know where, though. There are effect sizes, and these mean absolutely nothing to any normal human being. But down here, these are effects that do mean something. Here we get the mean difference and a confidence interval, and of course a p-value if you're into those things. Okay, so let's look. Comparing control to treatment 1, they have a difference of about 0.371. P-value tells us it's not significant. I would look over here at the 95% confidence interval. Look, it includes 0. Okay, they're not different. Same thing for control versus treatment 2. So where is the difference? Well, you're probably way ahead of me. You've looked at the p-value, you've looked at the confidence interval. There's no 0 here. They're all negative. And who are we comparing? Treatment 1 and treatment 2. That makes sense. We go back up to our box plot. Hey, looky there. Those are the most different. And that's where we found our difference. So there's one way of running a one-way analysis of variance. The other option is to use the general linear model. And this is far more flexible. Let's go here now, analyze, and instead of stopping here, compare means and proportions, general linear model. Univariate. Because again, we have one variable in this week. Next week, it'll be multivariate, but not now. No. Univariate. Okay. Weight would be my dependent variable. And look, this doesn't make me recode. I can use group just as it is. I don't have to recode. It's smart enough to know. And I'm using this as a fixed factor here because I'm going to assume that the effect of the different treatments is indeed fixed. That's what I want here. Now I need to define my post hoc tests. Yet again, you'll notice we have the same options available to us. Now they're grayed out, of course. I need to tell it I'm going to run post hoc tests across different levels of the group. And again, I'll just use good old Bonferroni. It's very simple. You'll find that this agrees with all the others. Heck, let's click one and we'll make sure it does. We'll get Tukey in there. Okay. So I'm good with that. Right, so we've defined our post hoc tests. And what we can do is go ahead and click OK. And what do we get? We get identical results. Hey, what's my F statistic for the analysis of variance? 4.846. What is it for my general linear model? The exact same thing. Isn't that wonderful? The effective group is indeed significant. Okay, so there's some difference across the groups. My post hoc tests are shown down here, right? And I've got my Tukey, I've got my Bonferroni, and it doesn't matter which one you use, it's still treatment 1 versus treatment 2 that is significant. Yes, the confidence intervals vary slightly. Notice with my Tukey, I'm going from about negative 0.156 to about negative 0.17, as opposed to negative 0.158 to negative 0.15. Still, they don't include 0. They agree with each other. So it's up to you which one you want to select. No biggie. But look, we've now run a one-way ANOVA 2 different ways. I suggest using the general linear model, but You go ahead and do whichever one works for you. They're going to give you the same results. In fact, look up here at your confidence intervals. They are identical whether you use the ANOVA option or the generalized linear model. What's nice about the generalized linear model is it tells you, hey, about how good of an explanatory variable is group. It gives you the r squared, or more importantly, the adjusted r squared value. How much variability of weight is explained by differences between the groups? Only about 21%. So there's probably a whole lot more that explain the differences in plant height than just the growth conditions that we varied in this example data set. Okay, so in this case we have run an analysis of variance and a t-test because we had, well, normal data that were measured on interval and ratio scales. Let's go to another data set. So for this, I'm going to clear this junk out of the way. I'll just go ahead and get rid of that. And let me run back to my data sets. What about this? So we've got the apply data set. And there's a lot of things in here, and we'll come back to this one in later lectures. Here, I just want to see, does the likelihood that someone applies to graduate school differ based on parent education, whether the parent, one or both parents went to graduate school and got a degree, or didn't. That's the 1 and 0. So I'm going to highlight all of these data. I'll copy, and I'll simply paste into SPSS. So I've got all my values here. Clearly, I'm going to need to do a recoding here. First, I want to rename things so they make sense. I'll call the likelihood of application likelihood, and I'll call the parent education parent ed. This is, of course, nominal, even though it's a bunch of numbers. They're just names for things. And this is actually ordinal, this likelihood. But what I need to do is code it. So we go to our data view so I know what I'm working with. Okay, so likelihood. I need to recode, and I'm going to use the same variable. I don't want to make a different variable. I'm going to recode into the same variable, and it's going to be likelihood. And let's specify the old and new values. Okay, so the old value of unlikely, I'm going to make now 1. And the old value of somewhat likely, I will make 2. We'll add that there. And finally, the old value of very likely, I want to make 3. That's about it. I click OK, and looky there, we've recoded it. How nice. Everything's still there, not missing anything. Okay, cool. We can scroll on down. It's all a bunch of 1s, 2s, and 3s. We go to our variable view. We've got our 1s, our 2s, and our 3s. Okay, good. So now I know I can't run a t-test. I can't run an ANOVA, right? I need to do some kind of non-parametric test. So I go to Analyze, Non-Parametric Tests, Independent Samples. Okay. Here, I don't want to do the automatic stuff. We'll just go to Fields. And what am I testing? Well, I'm testing likelihood. Oh, it's complaining about storing again. Okay, hold on. Let's go here and type. Let's call it numeric. Okay. So we're in numeric. Oh, let me make sure it's still ordinal. Great. Okay. All right. So we'll go back, analyze non-parametric tests, independent samples. Likelihood is in my test field. Okay. Parent ed would be my groups. Let's go to settings, And let's customize it here. I want to do a Mann-Whitney because it's just 2 samples. And I do want to select this confidence interval estimate. This probably won't be too meaningful here, but whenever we have greater variability of our measurement there, this will be more informative. So let's go ahead and run. Alrighty, we've got our parametric test here. Hey, look at that. Okay, so the p-value is far less than 0.05, so we reject the null. In other words, the medians are different. The likelihood of applying to graduate school differed based on whether the respondent had a parent with a graduate degree or not. Before we take a look at anything else, let's look at this plot here that shows the frequency of the ones. Unlikely to apply, somewhat likely, and very likely. Notice, a whole lot of ones here, and this kind of drops off as we become more likely to apply to graduate school. So students on the left would be those who had parents that neither of which had a graduate degree. Most common answer, unlikely to apply to graduate school. On the other hand, those students on the right here were those that had a parent who had a graduate degree, 1 or more, and their most common answer was somewhat likely to apply. Is the median of 1 different from the median of 2? Yes, absolutely it is. And so we have our confidence interval up here anywhere from, well, probably somewhat close to 0, but not quite 0, to -1. Okay, so it's somewhere between a 0 up to a 1-point change. We don't think there's a 2-point difference in these medians, probably just a 1-point. And this is the same plot, right? This is just showing us, without separating the groups, what's the frequency of 1s, 2s, and 3s for the likelihood, and what's the frequency of parent education, being no graduate education on the left, graduate education on the right. So from this, what we can conclude is that students whose parents have a graduate degree are more likely to say they will apply to graduate school. Now, the confidence interval isn't too terribly informative in this case. Why don't we go back to our plant growth data to take a look at a slightly more informative set of confidence intervals. So we'll clear that. I'll put this back in and pretty quickly get us to where we want to be. Oh, we might be upset over that. I'm not sure, but we'll cross that bridge when we come to it. Okay, so the fields here, we don't have that. Weight and group. All right, settings. We're going to do a Kruskal-Wallis. So this is the non-parametric version of the one-way ANOVA. And we'll leave everything else checked. I don't think SPSS is going to be okay with this. Let's see what they give us here. Oh, nice. It is indeed okay with it. How lovely. Okay, so here's our non-parametric output here. So we've got our Kruskal-Wallis test. Hey, we should reject the null, just like we did with the ANOVA. Excellent. Okay, we go down, we see our box plot, and we get our pairwise comparisons. This is what we're after. Okay, we get our test statistic, we get our adjusted p-values. What's significant? Treatment 1 versus treatment 2. Okay, that's the only one that mattered. Where's my confidence interval? Not here. So SPSS is a little hokey to work with in this case, but we can get around that. So if you do want to get pairwise comparisons here, we have to make another variable. And so what we'll do here is make a variable, and I'll just specify, you know what, let's not do this manually. We're not cavemen. I'm going to now clear that out. Let's transform we'll recode into different variables. So I want to make a new variable here based on group. And the old value of con, I want to make a 1. And the old value of treatment 1, I want to make a 2. And we'll call this con treatment 1. We'll click OK. And notice now we've left all of treatment 2 out. That's going to allow us to run a pairwise comparison between control and treatment 1. Looking over here at my stats, though, I don't care about that. I care about treatment 1 versus treatment 2. So now we need to practice again. We're going to recode into different variables. Again, group. What we're going to name this is now treatment 1, treatment 2. You can call this whatever you want. I'm just labeling it in a way that makes sense to me. I'll remove all my old stuff, and let's make treatment 1 be 1 and treatment 2 be 2. We'll click OK. We see what we end up with, and now control is left out. We have a value of 1 for treatment 1, a value of 2 for treatment 2. I know, kind of long-winded, right? So now we can go to analyze non-parametric tests, independent samples, for the third time. I'm going to go back to fields. I don't want to use group. I want to do the treatment 1 versus treatment 2 variable. That'll give me my pairwise comparison. I'll leave everything else the same. I want the Kruskal-Wallis, I want the Mann-Whitney. This is what I'm really after, though, that 95% confidence interval. So now we run it, and we get ourselves a 95% confidence interval. So again, these two are agreeing. They're telling me to reject the null. There is a difference between treatment 1 and treatment 2. Here is what I want the confidence interval summary. I think that the medians differ by somewhere between 0.37 and 1.48. Notice 0 is not in there. So I'm able now to generate a 95% confidence interval using a non-parametric test. So whether I analyze using a one-way ANOVA, that would be back up here. We got our one-way ANOVA. Let's go to our post hoc tests here and look, what was my 95% confidence interval? 0.15 to 0.158. Going back here to the bottom. Right, not the same, a little narrower, but both are significant. Right, in one case we're assuming a normal distribution, normal curves, all that jazz. In another case we're not. That would be the non-parametric test. All right, we have one last type of data that we want to analyze, and that's if we have a continuous explanatory variable. Let's go back to our data sets. So we handle plant growth, we handle apply. Let's take a look at question type. So here we got multiple choice questions, short answer questions. And what I'd like to know is, based on somebody's multiple choice score, how well can we predict their short answer score? So let's highlight our data, copy it, and we'll paste this into SPSS. I'm going to clear this out of the way, and just as simple, we paste in there. Okay, let's do what we always do. We go to variable view. Let's name this. So I'm going to call this MC for multiple choice and SA for short answer. And both of these are scale measures. So I can't run an ANOVA or anything like that. In this case, what I have to do is simple linear regression. Can I predict short answer scores based off of multiple choice scores? Now, whereas before, when we look at our plant growth data, for example, box plots are really nice here. That's not going to work for us. What we need instead is a scatter plot. So let's now construct a graph just to see what this looks like. And you can use lots of different options here. They have some, chart builder things. The chart builder here. I just like to click on the older, just scatter, here. It's a simple scatter plot that we want. And we're trying to use multiple choice, so we'll put that on the x-axis, to predict short answer. Right, we look at our options. This is all fine. We're not going to worry about any of that. Everything looks good. We'll just click OK, and we get ourselves a fairly simple scatter plot. Here's my multiple choice. You can kind of see a trend here. I mean, it's not super strong. That's what you get with real data. But in general, those who had higher multiple choice scores tended to have higher short answer scores. And those who had the lowest multiple choice scores had the lowest short answer. Okay, great. It'd be nice if we could get some kind of a trend line in here. So I'm going to double click here. And this opens up a sort of nice to use chart editor. And if you have a look, you should find the add fit line. We'll click that. And look at that. It puts a nice fit line there. I never like where it puts the equation. So I'm not going to attach the label to the line. We'll get rid of that. We're going to get our slope and intercept later. We already have our r squared. The multiple choice answers explain about 12% of the short answer variability. Okay, so there's probably something else going on there. So here, I would like to see a confidence interval. So we'll click confidence interval for the mean. We'll apply that. And we get these curved lines. Obviously, where we have fewer data points at the extremes, the confidence interval gets wider. Closer to the middle, it's a little more narrow. Okay, and what we're really looking for here is, to make sure there's not a whole lot of overlap, right? That this low end of my confidence interval doesn't overlap with the high end. Okay, and it doesn't really look like it does. So I'm going to assume that we have a significant correlation, but let's take a look. And again, I have to tell it, no, don't put the label on there. It's kind of ugly. We'll close this. We'll close this. And now our plot is a little more meaningful. Maybe not the most beautiful plot, but this tells us we've got ourselves a positive correlation. Let's test for significance, though. So we'll go back here, go to Analyze, and we're going to go to Regression. We're going to do a nice little linear regression. Okay, my dependent variable in this case, short answer. My independent variable, multiple choice. Now, I'm not going to do any multiple blocks. This is useful if you're doing some sort of stepwise regression. We only have one variable. We don't need to worry about that. That's not very helpful for us here. Okay, so I'm going to click into statistics. I do care about this one. I do want confidence intervals for my regression coefficients. No doubt about that. I do want the model fit. This is good. I'm going to leave that alone. I'm just going to add some confidence intervals. I'll say OK. For plots, there are some plots that we want to see. We do want a histogram. That's kind of nice. The normal probability plot is also nice to look at. This is going to help us check some assumptions. And we want to take a look at the residuals on the y-axis. That is the difference between our prediction and the actual value. And the prediction on the x. Right, so this is going to generate a nice plot for us to look for the heteroscedasticity. In other words, the equal variance across all the levels of my predictor. We'll say continue. We'll say OK here. If you wanted to save the output of the regression, you could. So I'll go ahead and do that. I'll save the unstandardized here. You don't have to. I will do it. And we'll click OK. Now you'll notice what it does is make you a new variable. This is the prediction of my short answer based on multiple choice. And you'll see in some cases we're pretty close. In other cases, we're off by quite a bit. So not a perfect correlation by any means. Okay, let's take a look at what we have here. Our model summary. So we get an R value. That's my correlation coefficient. Look at that. We just ran a correlation. And the correlation is 0.349, so not particularly strong. This would be not quite moderate, a somewhat weak correlation, but something that we'd probably care about. If we look at our regression output here, the p-value is less than 0.05. Great, this is telling me that I have a significant correlation between multiple choice and short answer questions. We want to know now the strength of the relationship. So now we come down here to the coefficients. This is probably the most important table here. Constant, this is just an intercept. I don't really care about that too much. This is just saying, hey, we're going to start off with 38.696 points, and we're going to add about a half a point. Get that out of the way. About 0.549 points for every point of multiple choice points that we have. So if we get 10 points on the multiple choice, we'll take our intercept, 38.686, and we'll add 5.49 onto it. That is significant, and we can tell by looking at our p-value here, or more importantly, our confidence interval. Do I care about multiple choice? Well, yeah, probably. So for example, 1 is in my confidence interval. Okay, now why did I say 1? Well, that means for every 1 point increase in multiple choice, I might actually get a 1 point increase in short answer. I might care about that. That could be meaningful. So what we want to do is look for meaningful differences here in our confidence interval. If we see them, then hey, maybe we have a meaningful effect. And if we don't, well, maybe not, right? So it's very important to think about your possible range of true values in the confidence interval, right? And here's generally what we do. We look for 0. If there's 0, then heck, maybe nothing is going on. We can't reject the null. There's nothing to see here. This confidence interval doesn't have 0. Okay, after that we want to think, is there a meaningful value in here? And let's just say we've decided 1 is a meaningful value. Or heck, let's call it 0.5. 0.5 is a meaningful value. If I can get a half a point increase for every point increase on multiple choice, I feel pretty good about that. 0.5 is, of course, in the confidence interval, so I'd say there's a statistically significant, because 0 is absent, and potentially meaningful improvement in short answer performance when we improve multiple choice. And why is that? Because I can see that 0.5 or above is potentially true. Now, I can't say that it's clearly a meaningful change, because I also have to accept that I might only increase by 0.079 points. And that's just simply not a big enough effect for me to care about it. So the interpretation is a little nuanced. Is there a statistically significant effect of multiple choice on short answer? Yes. That's clear cut. Is there a meaningful relationship? Maybe. Part of my confidence interval is above my meaningful value, but part of it is below. So I can say there's a potentially meaningful relationship. Now let's say that 0.05 was my meaningful value. Well, all of my confidence interval is above that, and I would say there's a clearly meaningful difference. So it's really important to know what is a meaningful difference. That's going to help us interpret those confidence intervals. Always good to then look at your plots, make sure that this kind of looks normal. Okay, good. My residuals are pretty normal. Another way of looking at them is here in this PP plot. So here we have a nice straight line, and hopefully my dots are falling along it. They pretty much are. There's a little deviation right here, but it's not like we're seeing a completely different slope here, right? This would be problematic. My blue dots are close enough. I'm not overly concerned, right? Not a big deviation. I look down here at that scatter plot that we made. Here's my 0 line. And notice it's not like there's a clear slope. I don't see a big slope here. Let's go ahead and double click into there and let's add a trend line. And look at that. My trend line here, I'm going to get rid of the label, is pretty much horizontal. So there's no clear trend where as I have, larger predicted values, I'm deviating more or less than when I have the smaller predicted values. No, it doesn't matter if I'm on the low end or the high end or somewhere in the middle. I'm overestimating, I'm underestimating with about equal amounts. So that's what we want to see in this scatter plot showing the predicted value compared to the residual. Hopefully we get a nice flat line here, and this will agree with what we're seeing up here. Hopefully we're following along that straight line pretty well, and hopefully my histogram looks pretty close to a bell. It's not going to be perfect, but that's all right. Okay, and since this is our first week, I'm going to go ahead and do one of those checkpoints with you. And let's go checkpoint 2, just because I would kind of like to look at that one. Okay, we've got our exam scores in the first column, we got our class section in the second one, and we can see there's 2 sections here. There's a flipped section and a control section of a class. Were the exam scores different? Well, let's highlight this. We'll copy, we'll head over to SPSS, and we'll paste it in. I'm going to clear this junk out of the way, and I'm going to now go to my variable view and say these are my scores in the first column, and this is my section, class section over here. Scores are scale, go back, everything looks good. Scores over here, they're scale. Sections are just labels. And what I would like to do is figure out, is there a difference between these two? So for this, we have 2 groups. We're going to run ourselves a nice little t-test here. Very straightforward. So let's go here. We'll go analyze. Hopefully SPSS is not unhappy with anything we're doing here. We want control and flipped, and we'll probably have to recode things, and even then it'll probably still get pissed at us. Options, yes, 95% confidence interval, please and thank you. Okay, let's see if everything's right with the world. Excellent. Nobody's upset with us. Okay, so we ran that. Boom, we got a t-test. Can we assume equal variances? Yes, absolutely. Should be, I don't know, that's a judgment call. Hey, look, my confidence intervals are like the same, so it doesn't matter. It goes from about 4.41 to 2.73, going from negative to positive. Okay, so let's think about that confidence interval. Here we're going from negative 4.41 to positive 2.73. Do these groups look different? Well, let's see what they look like. Why don't we go here to graphs, and let's go with box plot, simple. And our scores are going to be grouped by the section. Let's go ahead and put that in. Do these look different? Yet not really, right? Largely these boxes are laying right on top of one another. Maybe the control's a little higher, maybe the median's a little higher in the flipped. That has canceled out, as we can see. So what we can find here is when we look at the means, these are largely identical, maybe slightly higher in the flipped section than the control. Let's interpret our confidence interval. Does this include 0? Absolutely. So we have to accept that 0 is a possible true value for the difference. In other words, the difference is not statistically significant. Looking at our p-value, this agrees. This is not less than 0.05. So the difference in exam scores is not statistically significant. Now, is it potentially meaningful? Let's say we have a 1 point difference. That's what I'm going to call potentially meaningful. In that case, yeah, it's potentially meaningful, but it's potentially meaningful in both directions. Negative favors the flipped class. Positive favors the control. I have -1 and +1 in my confidence interval. That means I have to accept that there might be a meaningful advantage for flip. There might be a meaningful advantage for control. Let's take a more reasonable value. 5 percentage points. That's half a letter grade. That to me would be a meaningful change in exam scores. If we use 5 points, notice I don't see -5, I don't see +5. So there is no reason to conclude that there could be a meaningful difference between these two groups. So it's neither statistically significant nor academically meaningful. Why is it not statistically significant? Because there is no 0 in my confidence interval. Why is it not academically meaningful? Because I don't see any reason to believe that there could be a 5-point difference favoring either flipped or control sections. So the exam scores are pretty much the same, and that is backed up with this box plot here. All right, at this point I'm going to stop the video. Now, if you find that something here hasn't quite made sense and you want me to talk further about it, make another video to cover that, or just give you a written answer, you can do that by going back to the class website, scrolling down to this questions box here, and submitting whatever your question is. It'll pop up down here and I'll write an answer. If you'd like me to make a recording, put up some illustrations of things, absolutely I can do that. You just have to ask for it. I suggest that you, while watching this video, follow along, pause when needed, run the analyses that we did, and then click on into this checkpoint assignment here. This should be working. Let me click it. Great. You should be able to enter your UEID. That's all the stuff before @evansville.edu. Click next and you'll be able to look at all the questions. All it's going to ask you to do is exactly what we just did. Go into SPSS, generate a confidence interval, look for 0. If you see 0, there is no statistically significant difference. After that, look for whatever value is meaningful. I will tell you what it is so that we're all on the same playing field. If you see that value, then you have a potentially meaningful difference. If my confidence interval excludes that value, I have no reason to believe that there's a 5-point difference here, for example. There is no meaningful difference. If you find yourself lost along the way, please use the questions box. The whole point of checkpoints is to make sure you are getting it. So if you have a question, even on a checkpoint question, put it here. I'm here to help you with it, okay? This is not something you need to do on your own. I don't expect you to do this on your own. Use the questions box. I'll get an email, I'll respond, and I will help you as best I can. If you want a one-on-one, schedule that with me. Next week, what we're going to be doing is going through multiple explanatory variables, doing largely the same thing, but now we'll have a couple of variables that we might care about, and we'll see how to do that in next week's video. All right, make sure you tell me how I can help you so I can do so. Otherwise, you'll see me next week.